Welcome back to Sleepy Science Facts. Today, we continue our peaceful journey into the Milky Way, Part 2. In this chapter, we have explored dark matter, the invisible sculptor of the Milky Way. We have seen how it governs the galaxy's rotation, shapes its structure, and connects it to the broader cosmic web. We have examined the evidence for its existence, the experiments that seek to detect it, and the profound implications of this hidden mass. Dark matter is a reminder that much of the universe remains unseen, yet its influence is undeniable, a silent architect guiding the Milky Way and the cosmos beyond. Cosmic time, the age and history of the Milky Way. To understand the Milky Way is to understand time on a scale that stretches far beyond human experience. Our galaxy is not static. It is the product of billions of years of cosmic evolution, a living archive of creation, destruction, and transformation. Every star, every cluster, and every gas cloud carries the memory of events that occurred long before Earth existed, long before humanity began to gaze at the night sky in wonder. Astronomers estimate that the Milky Way formed approximately 13.6 billion years ago, not long after the Big Bang itself. The earliest building blocks were dense clumps of dark matter and primordial gas, which coalesced to form the first stars. These stars, massive and short-lived, forged the first heavy elements, carbon, oxygen, iron, through nuclear fusion, seeding the galaxy with the material needed to form planets and life in later generations. In this way, the Milky Way's earliest epochs set the stage for everything that would follow. Tracing the age of the galaxy relies on multiple lines of evidence. Globular clusters, dense spheres of ancient stars orbiting the galactic halo, are among the oldest known objects, with ages exceeding 12 billion years. These clusters serve as living fossils, preserving the chemistry and dynamics of the early Milky Way. By analyzing the light of these stars, their elemental abundances, and their motion, astronomers reconstruct the conditions of the primordial galaxy, revealing the processes that shaped its formation. Stellar populations act as markers of galactic history. The oldest stars, poor in heavy elements, indicate a time when the universe had only begun to enrich itself. Younger stars, found predominantly in the disk and spiral arms, reflect the ongoing cycle of star formation, fueled by gas enriched by previous generations. By mapping these populations across the galaxy, scientists can trace the sequence of star formation, mergers with smaller galaxies, and periods of quiescence, assembling a detailed timeline of the Milky Way's evolution. Cosmic time also reveals the dynamic processes that have shaped the galaxy's structure. Over billions of years, the Milky Way has grown through the accretion of gas and mergers with dwarf galaxies. Stellar streams, such as those from the Sagittarius dwarf galaxy, are remnants of these interactions, frozen in motion yet telling a story of consumption and transformation. The distribution of elements across the galaxy, too, reflects these ancient processes, revealing pockets of enrichment and regions still dominated by primordial material. Observations across multiple wavelengths allow astronomers to peer into different eras of the Milky Way's history. Infrared imaging penetrates dust-laden star-forming regions, revealing ongoing creation. X-ray and gamma-ray observations highlight remnants of past stellar deaths, supernova explosions that enriched the interstellar medium. Radio observations trace hydrogen gas, the raw material for future stars, connecting the galaxy's past to its future. Together, these data reveal a continuous narrative spanning nearly the entire age of the universe. Understanding the Milky Way in cosmic time places humanity in perspective. The Sun, a relatively young star at approximately 4.6 billion years old, is a latecomer in the galaxy's vast history. Earth itself is a tiny chapter in this grand narrative, appearing long after the first stars had lived and died, and yet existing at a moment when conditions allow life to flourish. Cosmic time reminds us of the fleeting nature of human existence, while also highlighting the continuity of the galaxy, a structure that endures across epochs. In this chapter, we have explored the age and history of the Milky Way, tracing its origins from the first stars to the present day. We have seen how globular clusters, stellar populations, and chemical abundances serve as markers of cosmic time, revealing a galaxy that has grown, evolved, and transformed over billions of years. The Milky Way is not merely a collection of stars. It is a living chronicle, a cosmic archive in which the passage of time is written in light, motion, and elemental composition. To study it is to study time itself, on a scale that humbles and inspires, connecting humanity to the vast, unfolding history of the universe. The Milky Way in the cosmic web, our place in the universe. The Milky Way is vast, yet in the cosmic expanse, it is but a single thread in a tapestry that stretches billions of light years. To understand our galaxy fully, we must step back and consider its place in the universe, among the countless galaxies that populate the cosmos, and within the intricate cosmic web that binds matter, energy, and time together. The Milky Way resides in the local group, a gravitationally bound collection of over 50 galaxies, dominated by two giants, our own spiral and the Andromeda Galaxy. These galactic neighbors are not static. They interact subtly, their mutual gravity guiding orbits, triggering tidal streams and shaping their halos. Smaller dwarf galaxies orbit the Milky Way, some already disrupted and absorbed, leaving behind stellar streams that weave through the halo as testament to a dynamic past. Even at this local scale, the Milky Way is part of a living, evolving community of galaxies. Beyond the local group lies the local supercluster, or Laniakea, a vast assembly of thousands of galaxies stretching over 500 million light years. The Milky Way is but one node in this immense structure, flowing along the gravitational currents of dark matter that form the cosmic web. These filaments and voids define the large-scale structure of the universe, channeling matter and energy, influencing galaxy formation and evolution, and connecting our tiny galactic island to the broader cosmos. Comparisons with other galaxies illuminate the Milky Way's uniqueness and commonality. While our spiral structure is elegant and familiar, countless other galaxies take forms both similar and extraordinary. Elliptical giants, irregular dwarfs, starburst galaxies ablaze with creation. Some are isolated, quietly aging, while others collide and merge, igniting waves of star formation and cosmic upheaval. By studying these galaxies, astronomers understand the Milky Way's past and anticipate its future, placing it within the universal continuum of galactic life cycles. The Milky Way also serves as a laboratory for understanding cosmic phenomena at all scales. Supermassive black holes, pulsars, molecular clouds, and dark matter halos are not unique to our galaxy. But here, we can observe them in unparalleled detail. The motions of stars, the distribution of elements, and the patterns of star formation provide a model for interpreting distant galaxies. Every insight gained in the Milky Way echoes across the universe, informing our knowledge of galactic evolution, cosmic structure, and the physics that governs it all. The philosophical implications of this perspective are profound. Humanity exists on a small planet orbiting an unremarkable star in one spiral arm of a vast galaxy, itself a single node in the immense cosmic web. Yet within this perspective lies both humility and wonder. The Milky Way connects us to the universe. Its history mirrors cosmic evolution. Its structure reveals universal processes, and its dynamics illustrate forces that shape all matter and energy. Observing the Milky Way within this cosmic framework reinforces our sense of interconnectedness. The galaxy's interactions with neighbors, its place within Laniakea, and its adherence to universal laws of gravity and physics demonstrate that the universe is a coherent, evolving system. Every galaxy, every star, every photon is part of a vast, intricate pattern, a grand cosmic dance choreographed over billions of years. In this chapter, we have explored the Milky Way in its cosmic context, examining its role within the local group, its place in the cosmic web, and its relationship to other galaxies. We have seen how observations of our galaxy inform universal understanding, and how its motions, structures, and interactions connect it to the broader cosmos. The Milky Way is not isolated. It is a participant in a vast cosmic story, a single yet integral character in the epic narrative of the universe. Exploring the Milky Way, humanity's journey to understand our galaxy. For as long as humans have gazed upward, the Milky Way has inspired wonder. Yet it is only in the last century that technology has allowed us to move beyond mere observation, to explore, measure, and understand the galaxy in detail. This journey, from naked eye stargazing to sophisticated space missions, represents the relentless human quest to comprehend our place in the cosmos. Early telescopes revealed that the Milky Way is not a cloud, as once believed, but a vast collection of stars. Galileo's pioneering observations in 1610 opened the first window, allowing humanity to glimpse the countless suns forming a luminous band across the sky. Subsequent centuries brought increasingly powerful instruments, enabling astronomers to catalog stars, star clusters, nebulae, and the motion of celestial bodies. Yet it was the advent of space-based observatories that truly transformed our understanding. Satellites like the Hubble Space Telescope provided unparalleled clarity, capturing distant star-forming regions, dense clusters, and the swirling gas clouds of the galactic center. Infrared observatories, such as the Spitzer Space Telescope, penetrated dust-obscured regions, revealing previously hidden stellar nurseries. Missions like Chandra and XMM Newton opened the X-ray window, exposing the violent high-energy phenomena that punctuate the galaxy: black holes, supernova remnants, and pulsars, illuminating processes invisible to optical telescopes. One of the most transformative projects is the Gaia mission, launched in 2013. By mapping the positions, distances, and motions of over 1 billion stars with unprecedented precision, Gaia provides a three-dimensional blueprint of the Milky Way. Its data reveals spiral arm structure, stellar streams, and the subtle movements of stars influenced by dark matter. Gaia allows scientists to reconstruct the Milky Way's history and predict its future, essentially turning the galaxy into a living laboratory for understanding stellar dynamics and galactic evolution. Humanity's exploration is not confined to observation alone. Radio telescopes such as the Very Large Array and Arecibo Observatory map neutral hydrogen, tracing the structure and motion of gas clouds across the galaxy. These observations illuminate the invisible scaffolding that shapes star formation, the distribution of dark matter, and the flow of material through spiral arms. Combining radio, infrared, optical, X-ray, and gamma-ray data provides a holistic view of the Milky Way, revealing the galaxy as a dynamic system in constant motion. The future promises even greater discoveries. Missions like the James Webb Space Telescope, launched in the early 2020s, penetrate deeper into dust-laden regions, capturing infrared light from nascent stars and distant galactic phenomena. Plans for interstellar probes, while still conceptual, hint at humanity's potential to explore the galaxy in situ, to directly sample the interstellar medium, study nearby star systems, and perhaps even glimpse the first exoplanets in detail. Each technological advance brings the Milky Way into sharper focus, reducing the distance between human curiosity and galactic understanding. Exploration also connects with philosophy and culture. Observing and studying the Milky Way bridges the gap between awe and knowledge. It transforms the night sky from a backdrop of myths into a map of the universe, from a source of wonder into a laboratory for scientific discovery. Every observation, every mission, every dataset strengthens humanity's connection to the galaxy, revealing our intimate bond with the cosmos. Yet the Milky Way remains vast and mysterious. Even with decades of exploration and billions of dollars invested, we have charted only a fraction of its stars, mapped only portions of its gas and dust, and glimpsed only the tip of its dark matter halo. The galaxy challenges us to continue, to probe deeper, to question further, and to embrace the unknown. Its scale, complexity, and beauty demand curiosity, perseverance, and imagination. In this chapter, we have explored humanity's journey to study and understand the Milky Way. From early telescopes to space-based observatories, from mapping stars to probing interstellar gas, we have seen how exploration reveals both structure and dynamics, past and future. The Milky Way is a laboratory, a frontier, and a source of inspiration, connecting human endeavor with the grandeur of the cosmos. In our quest to know the galaxy, we are, in essence, seeking to understand ourselves and the universe we inhabit. The dynamic Milky Way, motion, rotation, and cosmic flow. Though the Milky Way appears as a static band of stars in the night sky, it is anything but still. Our galaxy is alive with motion, a vast, intricate dance of stars, gas, and dark matter. Over millions of years, the spiral arms twist, stars orbit the galactic center, and clouds of gas flow, collide, and collapse, giving rise to new generations of stars. To understand the Milky Way is to witness a cosmic ballet unfolding over eons. The galaxy rotates around its central supermassive black hole, Sagittarius A, completing a full revolution roughly every 225 to 250 million years. Our Sun, moving at an average speed of 220 kilometers per second, traces a path around the galactic center, carrying the solar system through spiral arms, past star clusters, and across clouds of interstellar gas. This journey, known as the solar orbit, means that Earth has passed through different galactic neighborhoods countless times, witnessing varying conditions in cosmic history. Spiral arms themselves are not rigid structures. They are density waves, regions of enhanced gravitational influence that trigger star formation as gas clouds enter and compress. Stars born within these arms gradually drift away, moving along orbits determined by the combined gravitational pull of visible and dark matter. Over millions of years, stars migrate from their birthplaces, mixing the stellar population and spreading the chemical elements that support planet formation and ultimately life. Gas and dust within the Milky Way are equally dynamic. Molecular clouds flow along the spiral arms, colliding and compressing to ignite bursts of star formation. Stellar winds from massive stars and shockwaves from supernovae sculpt the interstellar medium, creating bubbles, filaments, and cavities. This interplay between gas, gravity, and stellar activity shapes the galaxy on both small and grand scales, maintaining a balance between destruction and creation. Observations reveal that stars move in complex orbits, not simple circles. Some oscillate above and below the galactic plane, influenced by the gravitational pull of the disk and halo. Others trace elongated paths, evidence of past galactic mergers or interactions. Stellar streams, remnants of cannibalized dwarf galaxies, wind through the halo, carrying stars far from their origin. These motions preserve the history of the galaxy, encoding its evolution in trajectories, velocities, and chemical composition. Even dark matter participates in this cosmic flow. Though invisible, it forms a halo that dictates the gravitational potential of the galaxy. The motion of stars, gas clouds, and satellite galaxies is governed by the distribution of this unseen mass. Without dark matter, the rotation of the Milky Way would be chaotic. Stars at the outskirts would escape, and the spiral arms would unravel. The invisible hand of dark matter ensures coherence and stability in the dynamic system we call home. Time-lapse observations, both real and simulated, allow scientists to visualize the Milky Way's motion. Spiral arms twist and propagate, stars migrate across the disk, and clusters disperse slowly over millions of years. Supernovae erupt in brilliant bursts, while molecular clouds collapse to birth new stars. The galaxy is not static. It is a living, breathing system, constantly renewing itself, shaped by gravity, energy, and the relentless passage of cosmic time. This understanding also provides context for Earth's journey. As the Sun orbits the galactic center, it moves through different environments, sometimes encountering higher densities of gas and stars, other times traveling through quieter regions. These variations may influence cosmic radiation levels, the rate of comet impacts, and even the conditions for life on Earth. The dynamic nature of the Milky Way is, in subtle ways, intertwined with the history of our planet and the evolution of life. In this chapter, we have explored the dynamic motion of the Milky Way, from stellar orbits to spiral arm density waves, from gas flows to dark matter influence. We have seen how stars, gas, and unseen mass interact in a grand, cosmic dance, shaping the structure and evolution of our galaxy over millions of years. The Milky Way is not a static backdrop. It is an ever-changing entity, alive with motion and energy, a vast system in perpetual transformation, a testament to the restless, creative forces of the universe. Spiral arms and stellar nurseries, the Milky Way's luminous landmarks. The Milky Way's spiral arms are the galaxy's most striking features, sweeping gracefully outward from the central bulge in vast arcs of stars, gas, and dust. They are not merely decorative. They are bustling regions of creation, where the raw materials of the cosmos are transformed into brilliant stars, planetary systems, and cosmic phenomena that illuminate the galaxy. These arms, sculpted by gravity and density waves, are the dynamic arteries of the Milky Way, channeling matter and energy across its vast expanse. Each spiral arm contains myriad stellar nurseries, glowing clouds of gas and dust where stars are born. The Orion Arm, our galactic neighborhood, is home to some of the most famous of these regions. Within it lies the Orion Nebula, a luminous cloud of hydrogen gas illuminated by young, massive stars at its center. Here, gravity pulls the gas into dense pockets, collapsing to ignite nuclear fusion, creating new stars that will eventually disperse into the galaxy. Observing these nurseries allows us to witness the ongoing process of cosmic creation, a window into the life cycle of stars. Other arms, such as the Sagittarius, Perseus, and Norma arms, host similar regions, each with its unique characteristics. The Carina Nebula, for example, teems with massive stars, their intense radiation carving intricate structures into the surrounding gas. Star clusters, bound groups of young stars, shine brightly within these regions, illuminating the surrounding clouds and providing laboratories for astronomers to study stellar evolution, chemical composition, and dynamics. Star-forming regions are not uniform. They are sculpted by the interplay of gravity, radiation, and turbulence. Stellar winds and supernova explosions shape bubbles, filaments, and pillars within the clouds, triggering new waves of star formation in adjacent regions. This cascading effect creates a chain reaction of birth and renewal, ensuring that the galaxy remains a vibrant, evolving system. Each spiral arm is a tapestry of these processes, a living chronicle of creation that spans millions of years. Embedded within the spiral arms are molecular clouds, vast reservoirs of cold hydrogen molecules, the raw material for star formation. Observations in radio and infrared wavelengths reveal these hidden structures, showing where future generations of stars will emerge. The interplay between these clouds, existing stars, and dark matter structures determines the pattern and density of new star formation, influencing the evolution of the Milky Way on both local and global scales. Clusters of stars within the arms serve as markers of galactic history. Young open clusters, rich in heavy elements, trace recent star formation, while older clusters provide clues to the past dynamics of the galaxy. Globular clusters, although predominantly located in the halo, offer complementary insights, connecting the history of the spiral arms with the broader timeline of the Milky Way's evolution. Famous nebulae also act as laboratories for understanding chemical evolution. The Carina Nebula, Eagle Nebula, and the Lagoon Nebula exhibit complex chemistry, including molecules such as carbon monoxide and organic compounds. Studying these regions allows astronomers to understand how elements produced in previous generations of stars are recycled into new stellar systems, seeding planets with the potential for life. The spiral arms also influence the motion and distribution of stars and gas. Density waves act as traffic patterns, slowing stars and gas clouds as they enter, compressing material, and triggering bursts of star formation. As stars age, they drift away from the arms, blending with the galactic disk. This process continually renews the galaxy, maintaining the balance between star birth and dispersal, and shaping the luminous patterns that define the Milky Way. In this chapter, we have explored the Milky Way's spiral arms and their stellar nurseries. We have seen how gravity, radiation, and turbulence combine to sculpt nebulae, ignite stars, and recycle matter throughout the galaxy. The arms are more than structure. They are engines of creation, luminous threads in the cosmic tapestry, and dynamic markers of the galaxy's evolution. By observing and understanding these regions, we witness the Milky Way not as a static band of stars, but as a living, breathing system, vivid, evolving, and endlessly captivating. The future of the Milky Way, collisions, transformations, and cosmic destiny. The Milky Way is not a static monument in space. It is a dynamic entity, evolving over billions of years. As we gaze at the stars tonight, we are witnessing a snapshot of a galaxy in motion, part of a continuum that stretches both into the distant past and far into the future. Understanding the Milky Way's destiny is to glimpse the grand tapestry of cosmic evolution, a story of collisions, transformations, and renewal. One of the most significant events in the Milky Way's future is its impending collision with the Andromeda Galaxy. These two spiral giants, each home to hundreds of billions of stars, are approaching each other at roughly 110 kilometers per second. Current calculations suggest that in about 4 billion years, the Milky Way and Andromeda will begin their slow, gravitationally orchestrated dance, merging over the course of billions more. This galactic collision is not a sudden cataclysm, but a gradual process. Stars, separated by vast distances, are unlikely to collide directly. Instead, the galaxy's gravitational fields will distort their shapes, triggering waves of star formation as gas clouds compress and collapse. The spiral arms will twist and intertwine, forming tidal tails of stars flung into intergalactic space. Over time, the two spirals will coalesce into a single, more massive elliptical galaxy, a profound transformation that reshapes their structure, dynamics, and appearance. The collision will also affect planetary systems, including our own solar system. While direct impacts are improbable, gravitational perturbations could alter orbits, ejecting some objects from their familiar paths or sending them into new trajectories. The Sun will continue to orbit the newly formed galactic center, witnessing a sky filled with new stellar neighbors, a cosmic dance unlike any ever seen by humanity before. Beyond the merger with Andromeda, The Milky Way's evolution is shaped by internal processes. Stars continue to form in spiral arms, while older stars die, enriching the interstellar medium with heavy elements through supernovae and stellar winds. Over billions of years, star formation will gradually decline as gas reservoirs are exhausted. The galaxy will age, the spiral arms fading, star clusters dispersing, and the luminosity of stars slowly dimming as the balance of creation and decay shifts. Dark matter continues to play a silent but critical role, maintaining the structural integrity of the galaxy and guiding the motions of stars and gas. Even as the visible matter changes, the dark halo ensures gravitational coherence, shaping the Milky Way's evolution and mediating its eventual interaction with Andromeda. The invisible framework persists, a testament to the enduring influence of unseen forces. The far future of the Milky Way extends beyond its merger with Andromeda. On timescales of tens of billions of years, stars will exhaust their nuclear fuel, stellar remnants will dominate, and black holes will remain as the primary custodians of mass. Galaxies will continue to merge and interact, eventually leaving behind a universe filled with faint stellar remnants and dark matter, a quieter cosmos where the Milky Way's legacy endures in altered form. Contemplating the Milky Way's future brings both humility and awe. We live in a brief moment, witnessing a galaxy in its vibrant, spiral phase, filled with active star formation, glowing nebulae, and dynamic motion. Yet this moment is but a fraction of its cosmic lifespan, a fleeting instant in the story of a system billions of years old and destined to continue evolving long after humanity is gone. In this chapter, we have explored the Milky Way's future, from its slow, inevitable collision with Andromeda to the internal transformations that will unfold over billions of years. We have seen how gravity, dark matter, star formation, and stellar death sculpt the galaxy's destiny, shaping its structure and dynamics. The Milky Way is not static. It is a living, evolving system, a participant in the grand narrative of the universe. Its future is both magnificent and inevitable, a testament to the ceaseless motion and transformation that define the cosmos. The Milky Way in human culture, stories, science, and inspiration. For as long as humans have looked up at the night sky, the Milky Way has been a source of awe, wonder, and imagination. Its luminous band, stretching from horizon to horizon, has inspired myths, guided travelers, and provoked questions about existence, creation, and the cosmos. Across continents and millennia, civilizations have interpreted this celestial river in ways that reflect both cultural identity and universal curiosity. Ancient peoples saw the Milky Way as a bridge between worlds, a pathway for gods, spirits, or the souls of the departed. The Greeks imagined it as the milk spilled by the goddess Hera, a divine trail in the heavens. The Chinese called it the Silver River, weaving stories of lovers separated by time and space. Native American tribes often interpreted it as a trail of the ancestors, guiding souls across the sky. These interpretations, diverse yet united by wonder, highlight humanity's instinct to find meaning in the cosmos. In the modern era, the Milky Way has become a laboratory for science, a canvas for understanding the universe. Telescopes, satellites, and space missions allow humanity to study the galaxy with precision. uncovering its structure, dynamics, and history. Observations of spiral arms, star clusters, nebulae, and dark matter reveal the processes that shape galaxies, connecting myth and imagination to empirical understanding. Science transforms the wonder inspired by the Milky Way into knowledge, yet the emotional resonance remains. Art and literature continue to draw upon the galaxy's majesty. Painters capture its luminous glow. Writers evoke its grandeur as a symbol of mystery and infinity. And musicians attempt to translate its cosmic rhythm into melody. The Milky Way serves as a bridge between objective observation and subjective experience, uniting human creativity with scientific insight. It embodies both the known and the unknowable, the measurable and the ineffable, reminding us that the universe is vast, beautiful, and profoundly inspiring. The Milky Way also plays a role in shaping philosophical thought. Its immensity and age provoke reflection on humanity's place in the universe, our temporal brevity, and the continuity of cosmic processes. By observing the galaxy, we confront questions of meaning, existence, and connection, recognizing that our story is a brief chapter in a much larger cosmic narrative. This perspective fosters humility, curiosity, and a sense of unity with the universe. In the realm of science, the Milky Way guides exploration and discovery. It is the reference point for understanding other galaxies, a laboratory for studying star formation, black holes, and dark matter. Its structure informs models of galactic evolution, while its dynamic processes provide clues to universal forces and interactions. By studying our own galaxy, humanity gains insight into the mechanisms that govern the cosmos, bridging imagination and empirical knowledge. Educationally, the Milky Way inspires new generations of scientists, astronomers, and explorers. Planetariums, observatories, and outreach programs bring the galaxy to life for students and the public, fostering curiosity and wonder. The same sense of awe that inspired ancient storytellers now motivates scientific inquiry, fueling missions to map stars, probe black holes, and understand the cosmic web. In this chapter, we have explored the Milky Way's profound influence on human culture, science, and imagination. From ancient myths to modern astronomy, from art and literature to philosophical reflection, the galaxy shapes both our understanding of the universe and our sense of connection to it. It is a symbol, a laboratory, and a source of inspiration, reminding humanity that we are part of something immense, beautiful, and ever-evolving. The Milky Way is more than a galaxy. It is a mirror of our curiosity, creativity, and longing to understand. As we study it scientifically and celebrate it culturally, we bridge the gap between observation and experience, between knowledge and wonder. It continues to guide us through time, across space, and within the human imagination, illuminating the path toward understanding ourselves and the cosmos we inhabit. Worlds among the stars, exoplanets, and life in the Milky Way. The Milky Way is not only a galaxy of stars, nebulae, and dark matter. It is a galaxy of worlds. Around countless stars, planets orbit in silent motion, hidden from naked eye view, waiting to be discovered. In recent decades, the search for exoplanets, planets beyond our solar system, has transformed our understanding of the galaxy, revealing that planets are not rare, but ubiquitous, scattered across the spiral arms and woven into the stellar tapestry of our cosmic home. The first confirmed exoplanets were detected in the early 1990s, orbiting pulsars in distant reaches of the galaxy. Soon after, discoveries expanded to planets circling sun-like stars, confirming that planetary systems are a natural byproduct of star formation. Today, thousands of exoplanets have been cataloged, varying in size, composition, and orbit. Some are gas giants like Jupiter, others rocky like Earth, and some occupy mysterious intermediate categories that challenge our understanding of planetary formation. Among these discoveries, the concept of the habitable zone, a region around a star where conditions may allow liquid water, has captured the imagination of scientists and the public alike. Planets within this zone, especially those orbiting sun-like stars, could potentially host life. Observatories such as Kepler and TESS have identified thousands of candidates, suggesting that the Milky Way alone may harbor billions of worlds capable of supporting life, a staggering prospect that redefines our place in the universe. The study of exoplanets employs diverse techniques. Transit observations detect the slight dimming of a star as a planet passes in front, revealing size and orbit. Radial velocity measurements observe the star's motion induced by a planet's gravitational tug, providing mass estimates. Direct imaging, still challenging, captures planets in infrared light, offering glimpses of their atmospheres and potential composition. These methods collectively allow astronomers to study not only the existence of planets, but also their potential for life. Beyond detection, the characterization of exoplanetary atmospheres has emerged as a frontier of research. Instruments such as the James Webb Space Telescope analyze starlight filtered through planetary atmospheres, searching for gases like oxygen, methane, and carbon dioxide, potential signatures of biological activity. While no definitive signs of life have yet been found, the possibility of life elsewhere in the Milky Way fuels both scientific inquiry and philosophical reflection. The Milky Way's billions of stars imply billions of planetary systems. From tightly orbiting rocky worlds to distant gas giants, from icy moons to temperate exoplanets, the diversity of environments is immense. Some may resemble Earth, others Venus or Mars, and some may exist in conditions beyond imagination. This richness of planetary landscapes hints at the extraordinary potential for life, evolution, and complexity across the galaxy. The search for life is not limited to exoplanets. Within our own solar system, moons such as Europa and Enceladus, with subsurface oceans beneath icy shells, are compelling candidates for microbial life. Studying these worlds informs our understanding of habitability and guides the broader search for life in the galaxy. Every discovery, from nearby moons to distant exoplanets, illuminates the possibility that life is a natural outcome of cosmic processes. The implications of life beyond Earth are profound. It challenges humanity's understanding of uniqueness, evolution, and interconnectedness. The Milky Way may be a galaxy teeming with life, each planet a potential story of biological emergence, adaptation, and survival. By studying these worlds, we confront the question of whether life is rare or common in the cosmos, a question that reshapes our understanding of existence itself. In this chapter, we have explored the Milky Way's planetary systems and the search for life among the stars. We have seen how exoplanets are detected, characterized, and analyzed, and how habitable zones define the potential for life. We have considered the diversity of worlds, the possibilities for microbial life, and the profound implications for humanity. The Milky Way is not merely a galaxy of stars, it is a galaxy of worlds, a cosmic archipelago of potential life, waiting to be explored, understood, and imagined. Cosmic hazards, supernovae, black holes, and gamma-ray bursts. The Milky Way, for all its beauty and wonder, is not a serene sanctuary. It is a galaxy of immense power, a place where forces beyond human imagination shape, destroy, and recreate. Among the most dramatic of these forces are cosmic hazards, supernovae, black holes, and gamma-ray bursts, phenomena that remind us of the dynamic and sometimes perilous nature of our galactic home. Supernovae are among the most spectacular events in the galaxy. When a massive star exhausts its nuclear fuel, its core collapses under gravity, triggering a violent explosion that can outshine entire galaxies for weeks. The shock waves from supernovae compress surrounding gas clouds, triggering waves of star formation, while their ejecta seed the interstellar medium with heavy elements, carbon, oxygen, iron, that are essential for planets and life. Supernovae are both destroyers and creators, reshaping their local regions and influencing the galaxy on grand scales. Gamma-ray bursts, rarer and even more energetic, release in seconds the energy that the sun emits over billions of years. These colossal explosions, often linked to massive star collapse or neutron-star mergers, send deadly radiation across vast distances. If one were to occur within a few thousand light-years of Earth, it could have catastrophic consequences for life. Yet these bursts also illuminate distant regions of the universe, offering scientists a glimpse of processes that govern the death of stars and the synthesis of heavy elements. Black holes, both stellar mass and supermassive, exert their influence quietly yet inexorably. At the heart of the Milky Way lies Sagittarius A, a supermassive black hole 4 million times the mass of the Sun. It governs the motion of stars in the galactic center, shaping the dynamics of the inner galaxy. Stellar mass black holes, remnants of massive stars, lurk throughout the disk and halo, occasionally accreting matter and emitting X-rays detectable across the galaxy. Their gravitational pull can disrupt nearby systems, yet they are also key players in galactic evolution, regulating star formation and mass distribution. Cosmic hazards are not merely distant curiosities, they influence the Milky Way's habitability. Supernovae and gamma-ray bursts may sterilize regions of space temporarily, while black holes sculpt stellar orbits and trigger star formation in surrounding clouds. These phenomena operate on scales and timescales far beyond human experience, yet their effects ripple through the galaxy, shaping the environments where stars, planets, and life emerge. Astronomers study these hazards with powerful instruments across multiple wavelengths. X-ray and gamma-ray observatories detect the high-energy signatures of black holes and bursts. Optical and radio telescopes trace supernova remnants, mapping the dispersal of elements and the compression of interstellar clouds. Through careful observation, scientists reconstruct the frequency, intensity, and impact of these events, understanding how they influence the galaxy's evolution and the conditions for life. Cosmic hazards also inspire reflection on humanity's place in the universe. We inhabit a small corner of the Milky Way, shielded by distance from many of these destructive events, yet our very existence is shaped by them. Elements forged in ancient supernovae are found in our bodies. The sun itself is a product of previous stellar generations. In this way, destruction and creation are intertwined, a testament to the dynamic balance that governs the galaxy. In this chapter, we have explored the Milky Way's cosmic hazards, from the explosive death of stars to the silent, gravitational dominion of black holes. We have seen how supernovae, gamma-ray bursts, and black holes influence galactic evolution, star formation, and the potential for life. These phenomena, while awe-inspiring and sometimes dangerous, are integral to the galaxy's story, revealing a universe in which creation and destruction are inseparable, and reminding us of the fragile yet resilient nature of life in a vast, dynamic cosmos. Cosmic companions. The Milky Way's satellites and dwarf galaxies. The Milky Way is not alone in its journey through the cosmos. It is accompanied by a retinue of smaller galaxies, dwarfs and satellites, that orbit, interact, and sometimes merge with their colossal host. These cosmic companions are more than passive neighbors. They are active participants in the galaxy's story, shaping its structure, enriching its composition, and leaving behind trails that reveal the history of gravitational encounters over billions of years. Among the most well-known companions are the large and small Magellanic Clouds, visible to the naked eye from the southern hemisphere. These dwarf irregular galaxies orbit the Milky Way at distances of roughly 160,000 and 200,000 light-years, respectively. Their gravitational interplay with our galaxy creates tidal forces that trigger star formation, distort stellar orbits, and generate streams of gas and stars. Observing these clouds provides insight into the processes that govern satellite-host interactions and the recycling of galactic material. Beyond the Magellanic Clouds lie dozens of smaller dwarf galaxies, faint and diffuse, often overlooked in the night sky. Some, like the Sagittarius dwarf elliptical galaxy, are in the process of being torn apart, their stars and gas stripped by the Milky Way's gravity. These stellar streams, remnants of galactic cannibalism, wind through the halo, serving as evidence of past interactions and providing a record of the galaxy's growth and evolution. Galactic mergers are central to the Milky Way's development. Throughout its history, the Milky Way has absorbed numerous smaller galaxies, each event leaving behind stars, clusters, and gas that contribute to the galaxy's mass and chemical diversity. Stellar streams, globular clusters, and variations in metallicity across the disk and halo are fingerprints of these interactions, allowing astronomers to reconstruct a detailed history of accretion and merger events. Dwarf galaxies also offer clues about dark matter, the invisible scaffolding of the galaxy. Their motions and stability are governed by dark matter halos, and studying their orbits and interactions helps map the unseen mass of the Milky Way. The faintest dwarfs, barely visible against the backdrop of the galaxy, may be dominated almost entirely by dark matter, serving as laboratories for understanding the fundamental nature of the universe. Interactions with satellites are not destructive alone. They can stimulate star formation and structural evolution. As dwarf galaxies pass through or near the Milky Way's disk, gravitational forces compress gas clouds, sparking new generations of stars. Spiral arms may be reinforced, tidal tails created, and stellar orbits subtly altered. These encounters contribute to the dynamic, ever-changing character of our galaxy. Observationally, modern surveys such as the Sloan Digital Sky Survey and Gaia have revolutionized our understanding of these companions. Detailed mapping of stellar streams, proper motions, and chemical signatures reveals the complex interplay between the Milky Way and its satellites. Simulations of these interactions allow astronomers to predict future mergers, including the eventual assimilation of remaining dwarfs, providing a glimpse of the galaxy's ongoing evolution. The story of the Milky Way's companions is a story of cosmic interconnectedness. Each dwarf galaxy, each satellite, tells a chapter of the larger narrative, a tale of gravity, interaction, and transformation. Their presence reminds us that galaxies are not isolated islands, but members of complex systems, growing, consuming, and evolving together in the vast cosmic web. In this chapter, we have explored the Milky Way's satellites and dwarf galaxies, uncovering their role in shaping the structure, star formation, and chemical composition of the galaxy. From the Magellanic Clouds to faint stellar streams, these companions illustrate the dynamic, interconnected nature of galactic evolution. The Milky Way is not solitary. It is part of a cosmic family, interacting, merging, and growing. A living system shaped by both its own dynamics and the gravitational influence of those who travel alongside it. Heart of darkness, Sagittarius A and the galactic center. At the very core of the Milky Way lies a region of profound mystery and immense power. Hidden behind thick clouds of interstellar dust, the galactic center is home to Sagittarius A, a supermassive black hole weighing nearly 4 million times the mass of our Sun. This singularity exerts a gravitational influence that orchestrates the motion of stars, shapes the dynamics of the inner galaxy, and governs the fate of gas and dust in its vicinity. Observing the galactic center is a formidable challenge. Dense interstellar clouds obscure visible light, concealing the region from traditional telescopes. Yet through infrared, radio, X-ray, and gamma-ray observations, astronomers have peeled back the veil, revealing a bustling environment of stars orbiting at extraordinary speeds, swirling gas clouds, and compact stellar clusters bound to the black hole's gravitational grip. Stars in the central parsec of the Milky Way, known as the S-stars, move at velocities of thousands of kilometers per second. Their tight orbits around Sagittarius A provide the most compelling evidence for the black hole's existence. By tracking these stars over decades, astronomers have mapped the gravitational influence of the black hole with remarkable precision, confirming predictions of general relativity in one of the universe's most extreme laboratories. The galactic center is also a site of extreme phenomena. Gas clouds spiraling toward Sagittarius A are heated to millions of degrees, emitting X-rays and radio waves. Occasionally, stars venture too close and are shredded by tidal forces in events known as tidal disruption events, producing brilliant flares of energy visible across the galaxy. Jets and winds emanating from the vicinity of the black hole stir surrounding material, regulating star formation and shaping the inner galactic environment. Star clusters near the galactic center, such as the arches and quintuplet clusters, contain some of the most massive and luminous stars in the Milky Way. These stars have lifespans of only a few million years, ending in spectacular supernovae that enrich the galactic center with heavy elements. The interplay between massive stars, gas, and the black hole forms a dynamic ecosystem where creation and destruction coexist in a delicate balance. Sagittarius A may also play a role in the broader evolution of the Milky Way. Supermassive black holes are thought to influence the growth of galaxies, regulating star formation and shaping galactic structure through energetic feedback. While the Milky Way's black hole is currently relatively quiet compared to active galactic nuclei in other galaxies, its past activity and potential future outbursts have likely left an imprint on the surrounding disk and halo. Studying the galactic center also offers a glimpse into the extreme physics of gravity, magnetism, and relativity. The environment around Sagittarius A challenges our understanding of matter and energy, from the behavior of plasma in intense gravitational fields to the acceleration of cosmic rays to near light speeds. Observing these phenomena provides a natural laboratory, unique in the universe, where theories of physics are tested against the universe's most extreme conditions. Beyond the science, the heart of the Milky Way captures the imagination. It represents the ultimate extremes of nature, a place where gravity dominates, stars race at incredible speeds, and light itself is warped. Yet it is also the anchor around which our galaxy revolves, a silent orchestrator of motion, a hidden force shaping the Milky Way's structure and evolution. In this chapter, we have explored Sagittarius A and the galactic center, uncovering a region of extraordinary power and complexity. From orbiting S-stars to massive star clusters, from tidal disruption events to energetic outflows, the heart of the Milky Way is a dynamic environment where gravity, energy, and matter converge in spectacular fashion. This central black hole, though invisible to the naked eye, exerts influence across the galaxy, shaping its past, present, and future, a true cosmic sentinel at the core of our celestial home. The invisible hand, dark matter and the Milky Way, beneath the luminous stars, glowing nebulae, and swirling gas clouds, lies a hidden realm that dominates the Milky Way's structure: dark matter. Invisible, elusive, and yet gravitationally potent, dark matter constitutes the vast majority of the galaxy's mass, shaping its rotation, binding its stars, and orchestrating its evolution. Though we cannot see it directly, its presence is felt in every motion, every orbit, and every gravitational interaction within the Milky Way. The first hints of dark matter arose in the 1930s, when astronomers observed that galaxies rotated in ways that could not be explained by visible matter alone. Stars at the edges of galaxies, including the Milky Way, moved much faster than expected. If only the observable stars and gas were present, these stars would have flown into intergalactic space. Invisible mass, it seemed, must provide the additional gravitational pull to hold the galaxy together. Decades of research have confirmed the presence of a massive, spherical halo of dark matter enveloping the Milky Way. This halo extends far beyond the visible disk, providing the gravitational scaffolding that maintains the spiral structure, regulates star motion, and anchors the orbits of satellite galaxies. Without this unseen mass, the Milky Way would be a far more fragile and chaotic system, incapable of sustaining the orderly rotation and structure we observe today. Dark matter is not directly observable, but its influence is measurable. The rotation curve of the Milky Way, which plots orbital velocity against distance from the center, reveals the gravitational pull of unseen mass. Stellar motions, gravitational lensing, and the dynamics of satellite galaxies all provide additional evidence, confirming that dark matter is pervasive, yet invisible. It is the silent architect of the galaxy, shaping its past, present, and future. Modern research seeks to understand the nature of dark matter itself. Leading theories suggest it consists of particles that interact gravitationally, but not electromagnetically, making them invisible to telescopes. Experiments on Earth and in space, from underground detectors to particle accelerators, aim to detect these elusive particles, to bring the invisible into the realm of understanding. Each discovery would illuminate the unseen framework that holds not only the Milky Way, but the entire universe together. The presence of dark matter also influences star formation. Its gravitational pull affects the motion of gas clouds, guiding their collapse and the subsequent birth of stars. Stellar streams from disrupted satellite galaxies trace the contours of the dark matter halo, revealing its shape, density, and distribution. By studying these subtle interactions, astronomers map the invisible, transforming abstract theory into tangible insight. The Milky Way's dark matter halo is a reminder of the universe's hidden complexity. It is a force that cannot be seen, touched, or directly observed, yet it dictates the motion of stars, the survival of spiral arms, and the ultimate fate of galactic interactions. It is a cosmic mystery that challenges our understanding of matter, gravity, and the very nature of reality. In this chapter, we have explored the Milky Way's dark matter, the invisible hand that shapes its structure and dynamics. From the rotation curves that revealed its presence to the ongoing search for its particles, dark matter is a fundamental yet enigmatic component of our galaxy. It reminds us that the universe contains more than meets the eye, that for every visible star, there is an unseen force at work, silently sculpting the cosmos and guiding the Milky Way on its journey through space and time. The Milky Way is not an isolated island of stars drifting alone through space. It is part of a grand cosmic community known as the Local Group, a collection of over 50 galaxies bound together by gravity, each with its own stars, planets, and secrets. Within this neighborhood, galaxies interact, dance, and shape one another over billions of years, weaving a complex tapestry of cosmic relationships that extends far beyond the spiral arms of our own galaxy. Among our closest neighbors is the Andromeda Galaxy, a spiral giant similar in size to the Milky Way. Located roughly 2.5 million light-years away, Andromeda is on a collision course with our galaxy, destined to merge over the next 4 billion years. Between the Milky Way and Andromeda lie numerous dwarf galaxies, some orbiting the giants like satellites, others wandering through intergalactic space. Each carries stars, gas, and dark matter, contributing to the gravitational landscape that defines our local cosmic environment. The Triangulum Galaxy, another prominent member of the local group, is smaller yet significant, a spiral galaxy approximately 1 million light-years away. Its interactions with both the Milky Way and Andromeda have likely influenced star formation, tidal streams, and the distribution of gas within the group. Beyond these giants lie faint dwarfs, many so dim they were only recently discovered by advanced surveys such as Gaia and the Sloan Digital Sky Survey. Each galaxy, no matter how small, plays a role in the dynamic evolution of the local group. These interactions are not merely passive. Gravitational tugs distort shapes, trigger star formation, and strip gas and stars from galaxies, leaving behind streams and tails that trace ancient encounters. The Milky Way's halo contains remnants of previous mergers, evidence that galactic cannibalism is a recurring theme in the life of a galaxy. Over time, these events build mass, enrich chemical composition, and subtly reshape the structure of the galaxy itself. On an even larger scale, the local group is part of the Virgo supercluster, a vast assembly of galaxy clusters forming a filament of the cosmic web. The Milky Way, Andromeda, and their companions drift along these filaments, influenced by the combined gravitational pull of countless galaxies. This cosmic web provides the large-scale structure of the universe, a framework within which the Milky Way evolves, interacts, and participates in the grand cosmic ballet. Understanding the Milky Way in this broader context transforms our perspective. It is not merely a spiral of stars suspended in darkness. It is a participant in a vast, interconnected network. Galactic interactions, mergers, and tidal forces are ongoing processes, shaping not only our galaxy's present, but also its distant future. By studying the motions and relationships of nearby galaxies, astronomers can reconstruct the history of the Milky Way, revealing the events that have built its mass, sculpted its halo, and enriched its stars. The cosmic neighborhood also offers insight into dark matter. The motion of satellite galaxies, stellar streams, and the rotation of nearby systems all reveal the presence of unseen mass on scales far beyond our galaxy. Dark matter binds the local group together, ensuring that these galaxies remain gravitationally connected while guiding their interactions over billions of years. In this chapter, we have explored the Milky Way's place within the local group and the larger cosmic web. From neighboring giants like Andromeda and Triangulum to faint dwarf galaxies and distant filaments, the galaxy exists not in isolation, but as part of a dynamic, interconnected system. Its past, present, and future are influenced by neighbors near and far, a testament to the universality of gravity and the intricate architecture of the cosmos. The Milky Way is at once unique and connected, a luminous thread woven into the fabric of the universe. Gazing into the galaxy, observing the Milky Way across time and technology, for millennia, humanity has looked up at the night sky, captivated by the luminous river of stars we call the Milky Way. Early civilizations interpreted its shimmering band as a divine pathway, a celestial river, or a trail of spirits. Ancient astronomers, using little more than naked eyes and simple instruments, began the first attempts to map its shape, orientation, and position across the heavens. Yet what was once myth and speculation has now evolved into a rigorous science, revealing the Milky Way in unprecedented detail. The development of telescopes transformed our understanding of the galaxy. Galileo Galilei, in the early 17th century, pointed his telescope at the Milky Way and discovered that it was composed of countless individual stars, rather than a nebulous glow as previously imagined. This realization marked a turning point, shifting the Milky Way from myth to measurable reality, and laying the foundation for modern astrophysics. Over the centuries, observational technology has advanced dramatically. Optical telescopes allow astronomers to see stars and nebulae with extraordinary clarity. Radio telescopes, such as the Arecibo Observatory, detect the faint emission of hydrogen gas, mapping the structure of spiral arms hidden behind dust clouds. Infrared and ultraviolet observations reveal warm and hot regions of star formation, while X-ray and gamma-ray instruments probe the most extreme environments, including black holes and supernova remnants. Space-based observatories have further revolutionized our view. The Hubble Space Telescope captured stunning images of nebulae and star clusters, while the Gaia mission measures the precise positions and motions of over 1 billion stars, creating a three-dimensional map of the galaxy. The James Webb Space Telescope, with its powerful infrared capabilities, peers into dense stellar nurseries and distant corners of the Milky Way, uncovering regions invisible to previous instruments. Each technological leap deepens our understanding of the galaxy's structure, composition, and dynamics. Mapping the Milky Way is a unique challenge. From our vantage point within its disk, we cannot see it in its entirety. Dust clouds obscure vast regions, and distance makes it difficult to ascertain true sizes and positions. Yet through multi-wavelength observations, astronomers reconstruct the galaxy's spiral structure, measure its rotation, and trace stellar populations. Sophisticated simulations combine these observations with physics models, allowing us to visualize the Milky Way in ways unimaginable just decades ago. Beyond imaging, spectroscopy allows scientists to probe the chemical composition, temperature, and motion of stars and gas. By analyzing light across different wavelengths, astronomers determine the metallicity of stars, revealing their ages and origins. Gas clouds, stellar winds, and supernova remnants are characterized, providing insight into ongoing processes that govern star formation, evolution, and the recycling of matter within the galaxy. The Milky Way has also become a laboratory for understanding the broader universe. By studying our own galaxy, astronomers develop models applicable to distant galaxies, whose details remain unresolved due to immense distance. Observations of stellar populations, dark matter distribution, and galactic dynamics in the Milky Way inform our knowledge of galaxy formation and evolution across cosmic time. Human exploration has extended beyond observation. Space missions have allowed us to measure cosmic rays, interstellar gas, and the local magnetic field, revealing the environment of our solar system within the galaxy. Robotic probes, satellites, and ground-based instruments collectively build a detailed picture, connecting the night sky seen by ancient observers to the complex, multi-dimensional galaxy we now understand. In this chapter, we have explored how humanity has observed and studied the Milky Way, from early naked eye astronomy to cutting-edge space telescopes. Each technological advance uncovers new layers of complexity, revealing the structure, motion, and composition of our galaxy. Observing the Milky Way is not just a scientific pursuit. It is a testament to human curiosity, ingenuity, and the enduring desire to understand our place in the cosmos. Through these eyes, we see the galaxy not as a distant abstraction, but as a living, dynamic, and awe-inspiring home in which we reside. The Milky Way as a cosmic laboratory, unlocking the secrets of the universe. The Milky Way is more than a collection of stars and gas. It is a natural laboratory, a living experiment in cosmic evolution. Within its spiraling arms and luminous core, processes unfold that illuminate the laws of physics, the origins of chemical elements, and the potential for life beyond Earth. Every star, every nebula, every black hole contributes to a vast experiment that allows humanity to probe the universe on scales both immense and infinitesimal. Stellar evolution is one of the most accessible phenomena for study within the Milky Way. From the youngest stars still embedded in their natal clouds to the oldest stars in the galactic halo, the galaxy contains a complete timeline of stellar birth, life, and death. Observing these stars in detail allows scientists to test models of nuclear fusion, energy transport, and the formation of planetary systems. The Milky Way is a laboratory where theoretical predictions meet observable reality. Star clusters, both open and globular, provide another avenue for discovery. Open clusters in the disk contain young stars born together, allowing astronomers to study their evolution under shared conditions. Globular clusters, ancient and tightly bound, preserve information about the early Milky Way, offering insight into the chemical enrichment, dynamics, and gravitational interactions of the galaxy over billions of years. By analyzing these clusters, scientists reconstruct the Milky Way's history and the processes that shaped its structure. Supernovae and stellar remnants are critical components of this cosmic laboratory. When stars die, they release energy, heat, and heavy elements, seeding the interstellar medium with the building blocks of future stars, planets, and potentially life. Observing supernova remnants, neutron stars, and black holes allows scientists to study the extremes of matter, gravity, and magnetic fields. The Milky Way provides a nearby environment where these high-energy phenomena can be analyzed in detail, informing models of stellar and galactic evolution across the universe. The galaxy's chemical evolution also tells a compelling story. By examining the abundances of elements in stars and gas clouds, astronomers trace the life cycles of matter through generations of star formation and death. Heavy elements like carbon, oxygen, and iron are produced in stellar cores and distributed through supernovae and winds, enriching the interstellar medium. This process connects directly to the conditions necessary for planets and life, highlighting the Milky Way as a laboratory for understanding the origin of the elements that make up our world. Black holes, from stellar remnants to the supermassive core, offer another frontier for experimentation. By observing how matter behaves near extreme gravity, scientists test the predictions of general relativity, study high-energy particle acceleration, and probe the dynamics of galactic nuclei. The Milky Way's central black hole, Sagittarius A, provides a unique nearby laboratory, allowing observations that are impossible in more distant galaxies. Astrobiology finds a natural stage in the Milky Way. With billions of stars hosting planets, the galaxy allows scientists to explore questions of habitability, planetary formation, and the potential for life. Observations of exoplanets, icy moons, and planetary systems inform our understanding of where and how life might arise, positioning the Milky Way as a testing ground for theories that extend across the cosmos. The Milky Way also serves as a laboratory for understanding large-scale cosmic dynamics. Spiral structure, stellar streams, and the motions of satellites reveal the interplay of gravity, dark matter, and galactic evolution. Simulations and observations together allow astronomers to reconstruct events spanning billions of years, testing the principles of physics in a real, dynamic system. In this chapter, we have explored the Milky Way as a cosmic laboratory, where stars, clusters, supernovae, black holes, and planetary systems collectively reveal the laws of nature. The galaxy allows us to study the processes that govern the universe, from nuclear fusion to dark matter dynamics, from chemical enrichment to the potential for life. Within its spiraling arms, humanity discovers not only the secrets of our galaxy, but the principles that shape all galaxies, all stars, and all matter across the cosmos. The Milky Way, a story of connection, time, and wonder. As we gaze upon the Milky Way, we are not merely observing a distant galaxy. We are witnessing a story that spans billions of years, a story written in light, gravity, and matter, in the births and deaths of stars, in the swirl of gas clouds, and the silent pull of unseen forces. The Milky Way is a chronicle of creation, destruction, and transformation, a living system in which every star, planet, and particle plays a part in the cosmic narrative. From its spiral arms to its dark halo, from the brilliance of star clusters to the quiet dominance of dark matter, the Milky Way is a microcosm of the universe. Its history tells of violent collisions and serene formations, of stellar nurseries and cataclysmic deaths, of invisible forces and observable wonders. Within this galaxy, processes that govern the cosmos are laid bare, offering humanity a laboratory to study, explore, and understand the principles that shape reality itself. Yet the Milky Way is also a mirror of our own existence. The elements forged in ancient stars became the building blocks of planets and, ultimately, life. The carbon in our bodies, the oxygen we breathe, the iron in our blood, all were created in the nuclear furnaces of stars long gone. In this sense, we are intrinsically connected to the galaxy, participants in a story that began long before our sun ignited and will continue long after we are gone. Humanity's curiosity has illuminated the Milky Way in unprecedented ways. Telescopes, Satellites and space missions have transformed the once mythical river of light into a mapped, measured, and analyzed galaxy. From the earliest naked eye observations to cutting-edge infrared and X-ray imaging, we have progressed from wonder to understanding. Yet the awe remains. Every new discovery inspires deeper questions, reminding us of both the vastness of the universe and our capacity to comprehend it. The Milky Way is not merely a physical entity. It is a source of inspiration, imagination, and reflection. It connects the scientific with the spiritual, the empirical with the emotional. Ancient myths and modern research coexist, each revealing a different facet of the galaxy's majesty. It teaches us humility, curiosity, and wonder, urging us to explore, to question, and to imagine beyond the boundaries of our terrestrial lives. Looking to the future, the Milky Way continues to evolve. Stars will be born and die. Galaxies will merge, black holes will consume and shape, and the cosmic dance will continue. Humanity, though fleeting in comparison, will observe, study, and reflect, forever seeking to understand our galaxy and our place within it. The Milky Way is a story still unfolding, a testament to the dynamic, interconnected, and magnificent nature of the universe. In this final chapter, we see the Milky Way as both a laboratory and a companion, a historical record and a source of inspiration. It is a galaxy of complexity and beauty, of extremes and subtleties, of mystery and revelation. It is our cosmic home, our teacher, and our muse. The story of the Milky Way is a story of connection between stars and gas, matter and energy, past and future, the universe and humanity itself. As we prepare to step back from this journey through our galaxy, we are reminded that the Milky Way is not just out there in space, it is part of us. It flows through our bodies, our understanding, and our imagination. It is the stage on which the universe performs its eternal play, and we, however briefly, are witnesses, participants, and storytellers of its grandeur. The Milky Way, our cosmic home, as we step back from the vast expanse of the Milky Way, from its spiral arms to its hidden halo, from the brilliance of newborn stars to the darkness of supermassive black holes, we are struck by a profound truth. This galaxy is not simply a collection of stars, gas, and dust. It is a living testament to time, energy, and cosmic evolution, a story billions of years in the making, in which we are an inseparable part. We have journeyed across star clusters and nebulae, traced the arcs of stellar streams, and glimpsed the invisible hand of dark matter. We have witnessed the violent deaths of massive stars, the silent power of black holes, and the dance of galaxies across the cosmic web. We have looked at exoplanets, pondering the possibility of life elsewhere, and seen that our sun, our Earth, and even our very bodies are forged from the remnants of long-dead stars. The Milky Way is not distant or abstract, it flows through us. We are, in a very real sense, children of the galaxy. Yet this journey is more than science, it is a journey of wonder. It is the awe we feel when a clear night sky reveals the river of stars across the heavens. It is the humility we experience when we contemplate the scale of time, the vastness of space, and the intricate, invisible forces that shape our cosmic home. It is the inspiration that drives us to explore, to seek understanding, and to imagine what lies beyond the limits of our vision. The Milky Way is a story of connection. Stars are born from clouds shaped by previous generations of stellar death. Planets may harbor life shaped by the delicate balance of energy, matter, and chemistry. Our human story, though fleeting, is intertwined with this grand galactic narrative. Every element in our bodies, every particle of dust in our atmosphere has a history written in the heart of the galaxy. We are not separate from the cosmos. We are participants in its ongoing creation, witnesses to its eternal unfolding. And yet, the Milky Way reminds us that life and matter are fleeting in the grand scale of time. Stars burn out, galaxies collide, black holes consume, and eons pass. But within this impermanence lies the beauty of existence, the transience that makes every moment precious, every discovery awe-inspiring, and every human reflection a thread in the larger tapestry of the universe. As we conclude this journey, we are left with both knowledge and wonder. We have seen the Milky Way not as a static image, but as a dynamic, evolving, and living system. We have traced its history, explored its structure, witnessed its violent and creative forces, and contemplated its future. And through it all, we have glimpsed our place within this vast, interconnected galaxy, a place both tiny and extraordinary, fleeting yet eternal in its connection to the cosmos. The Milky Way is more than a galaxy. It is a story of creation, destruction, and rebirth. It is a laboratory for understanding the laws of nature. It is a river of light across the sky, a source of inspiration for humanity, and a reminder of our origins. And as we lift our eyes to the heavens tonight, we realize that we are not merely observers. We are part of this galaxy, intimately linked to its past, present, and future. The Milky Way is our cosmic home, and in it we find both our beginnings and our destiny. So let us look up, let us wonder, and let us remember. Every star we see, every orbiting planet, every hidden remnant of a long-dead star tells the story of the Milky Way, and that story is, in many ways, our story too. Thank you for drifting through the Milky Way with us. Tonight, we learned how our galaxy formed, what lives at its mysterious core, and why its structure still puzzles astronomers around the world. If you enjoyed this gentle journey through space, don't forget to like, subscribe, comment your thoughts, and continue exploring with our next relaxing science video. Stay curious and stay dreamy here at Sleepy Science Facts.